Okay, let's just take this much of this graph. Okay? Now I'm going to draw that over here. Okay? Now, let's see, this point here is not sure really want a 1 unit.
What's
Okay, I'm
the
not gonna-
thingy with the cutoff thingy?
The what now?
The what?
What's the white thing you just drew?
The house, obviously. Duh.
This is supposed to be this. Okay? Now that, it turns out I don't want to do that one. I'm gonna do this one here. Because there's something with this one that doesn't get well illustrated. So I'm gonna do this little thing. Okay, now T is 10 here, and it's 13 here. Right? And the height here is 0.5, and the height here is, I'm going to go ahead and use decimal approximations. Approximately 0.87, that's the square root of 3 divided by 2 to 2 significant figures. Okay? And actually it isn't, because in this thing, okay, I'm not gonna do that. Ideally, to 2 significant figures, it would be 8.7, but I'm just gonna approximate it as 9. Just using our numbers, the numbers we've estimated, without relying on any fancy geometry or anything like that, okay? So what I see is that the value of this function from here to here changes from 5 to 9, while the t value changes from 10 to 13. So my question is, what's the average rate of change of y with respect to t? And I'm going to add just a little language to that. On the interval ten, 13. And that'll be the interval of the dependent variable, the horizontal variable, right? Now, are we familiar with this notation? With closed brackets, 10, 13 means the interval from 10 to 13, including 10 and 13. Okay? Okay, so what do you think the average rate of change is? Now, what do we mean by average rate of change?
How much it changes every time?
Huh?
How much it changes?
More than that, but that's part of it.
Change in, y's
I'm sorry, Morgan?
The change in y's over the change in x.
Well, yeah, the change in the dependent divided by the change in the independent. In this case, it'd be the change in y divided by the change in t, because this is t here, but it's, yeah, your answer is very good. Okay? So, it's the change in the value of the thing divided by how much the independent variable changes, right?
So 4 divided by 3?
Yeah. Now, is that difficult?
No.
Okay?
9 minus 5 is 4. Dependent over independent?
Yes. Or the change, when you say the rate of change of A with respect to B, change in A divided by change in B, right? Change of the first thing you say divided by the change of the second thing. Because sometimes you can't tell what's independent and what's dependent. And it doesn't always even have to be independent and dependent, but in most applications it is. So that's, what, 9 minus 5
Which is 4.
over 13 minus 10, which is 4/3. Okay? Okay. Now I'm going to go to white because it shows up a little better. Okay, some left altitude, I'm abbreviating the word altitude, okay? And here is what I'm going to call the right altitude because it's gone up on the graph, right? Now you got to be a little careful. What is this shape here? If I take the 4 sides here of this that enclose this area, what's the shape?
The trapezoid.
It's a trapezoid. How do you get the area of a trapezoid? Somebody gives you a formula and you use it, right?
Yeah.
No, you prove it geometrically. But it comes down to this. 2 of these sides are parallel, right?
Yeah.
You take the 2 sides that are parallel and you average them. What do you get if you average 5 and 9? 7. I'll give you a hint. It's a number halfway between 5 and 9. You can get that. Or if the numbers are nasty, you can add the 2 and divide by 2, right? Very easy to get the mean of these 2 numbers, right? And then you multiply that by how far it is from here to here, by how far it is between the 2 parallel lines, right?
7 times 3 is 21.
I'm sorry?
21.
Yeah, but that's not what's important, okay? What's important is that's how you reason out the area of a trapezoid, okay? And it has to be so, all right? And we'll probably prove that next time, but we're kind of short on time right now, so we're not going to, okay? I mean, it's very simple. You just go, I'll do it. You just go over to the midpoint here, and you trim this little triangle off here, and you flip it around, and it goes here, and now you have a rectangle whose dimensions are this distance divided by the number halfway between these. Okay? Very simple. Now, if you were taught geometry without being taught that little reconstruction, without being given scissors, of course you can't give scissors to 8th graders, you know, without posing it that way, I think you're doing the universe a disjustice, an injustice, disjustice. Okay? That's just my opinion, but you know, I'm right about pretty much everything, so that's probably true. Okay, now, don't believe that. Okay, does that make sense? Okay, you believe me? Okay, now the thing that's confusing about calling these altitudes is those are the bases of your trapezoid in geometry. The bases of the parallel sides. So when you get that silly formula that nobody needs if they've got common sense, you know, I looked at that thing, I said, what in the world is that? I said, well, oh, duh. Why did they give us a formula for something that obvious? Well, because some people, it's not as obvious. And they need to use a formula, and they should separate people that do from people that don't, so they can teach some of us geometry and teach other people how to use formulas, which is still a very important thing. But then people's feelings get hurt, and parents complain, you know. Okay, so anyhow, you got your left altitude, your right altitude, and I'm gonna call this the slope segment, okay? And I'm gonna call this the width, okay? Now, in geometry, this is the altitude of your trapezoid. It's from the parallel side to the parallel side. So I'm kind of switching the terminology around. So I'm going to call these left graph altitude and right, can't read it, but it's the word graph, right graph altitude and the graph width, to distinguish it from the geometry altitudes and geometry widths, and so forth, okay? Even though you don't have a width when you're talking about trapezoid. But we want to be careful that we don't mix the terminology too badly, okay? Okay, well then, in terms of right altitude, left altitude, width, what's the slope of that slope segment? Well, let's just go to the numbers. What's the slope of this segment from here to here?
4/3.
It's rise divided by run, okay? And that's exactly right. To go from 5 up to 9, you got to go up 4, right? And your run is from here to here. Well, that's the same as from 10 to 13. That's 4. So guess what? Where have you seen 4/3 before? It's the average rate of change, okay? And it's the slope. So the slope represents the average rate of change. Okay? Any objection? Nah, wouldn't do you any good. Okay, that's fine, that's good. Okay, so we now have this picture. We've got 10, we've got 13, we've got 5, and we've got 9. Now I'm going to put the 9 on this side because generally I label an altitude to the left of the segment. I didn't do that here, but coming around to some conventions that we want to use, we're going to do this. Okay? The slope is 4/3, and I'm going to put that in a box up over the slope segment. Got that? I don't want to see that number without the rectangle around it. Okay? It's a convention. It's just a convention we use in my classes. Okay? So if you do this out in polite society, they'll probably throw you out. Okay, you studied with Dave, get out of here. Okay, now, got that. That's the average rate of change. That's the approximate derivative. It's a calculus thing. Okay, and we'll see how that works. Okay? And we'll do just a little bit of that. Okay, what's the area of this trapezoid? Again?
49 square units.
Don't think so. Not?
Or
21.
Yeah, 21.
We figured that out a while ago when we trimmed this thing and reconstructed it into a rectangle, right? Okay? So if you understand this picture, you understand that the area is 21. Okay? So in labeling a trapezoid, a graph trapezoid, we put slope in a box, put area inside in a circle. Okay? So for points between here and here, our slope is an approximate value for the slope of the tangent line. Of course, for this interval, it's not much good because the tangent line is positive here, has a positive slope here, a negative slope here. It doesn't give you a lot of information. Okay? Also, the area of this thing is an approximation to the area underneath the curve. And that's called the definite integral of the function, and those are the two basic things that you study in calculus. We're not going to learn the rules for those things. We'll probably derive the rule for a quadratic function or something, let you know what that is. And you mostly pretty much do, but you got to get those graphs done. The things that I'm asking you to do for tomorrow. Okay? As I warned you, you got to know this for Tuesday. So if you ignored it for Monday because you were doing all this other stuff and you did an impressive amount of work, so I'm not complaining, but make sure you do that for Tuesday, okay?
Good point.
I'm sorry? Yeah, okay, whatever. Okay, so, now there's more, okay? As I said, for this trapezoid, really, the average slope, 4/3, doesn't give you a lot of information about what's going on at any point between here, right? Okay? Now the area is, yeah, I'd say the area of this thing, yeah. What percent of the area under the curve do you think is between this trapezoid and the curve? More or less than half. Total area under the curve, meaning all the area underneath this and above the interval down here. Is this part more or less than half of the total area? Well, do you have more area here or more area in the trapezoid?
Less than half.
Yeah, you have more area in the trapezoid, right? Do you have twice as much area in the trapezoid? Yeah. You have 4 times as much? Well, that's where it gets a little shaky, maybe even 3 times as much. But most of the area under the curve is in the trapezoid, right? Now we have, I told you how you can interpret slope as a rate of change. I haven't told you how you can interpret area, but we'll talk about that tomorrow. Okay, because that's a little more complicated. Just integration is a little harder than differentiation, as anybody who's taken even an applied calculus would know. Gets a little tricky. Okay, so anyhow, if we do a slightly smaller trapezoid, let's do this one. Okay? Now, what percent of the area under the curve, between here and here, is in the trapezoid? More than half? Well, you've only got this little sliver here that's outside the curve, right? So by making the trapezoid smaller, or less wide, okay, making the x-interval shorter, we've got a much better approximation to the area, right? Of course, we're not getting all the area from here to here. We do another trapezoid and add them up and get the area. But we're getting pretty close to having all the area under the curve, aren't we? That little sliver, I don't think is even 10%. So I think we've got at least 90%, maybe as much as 97, 98%, probably not 98, maybe 97. Maybe not, at least 95, in my opinion. Okay? So we've got most of the area under the curve here, right? So that trapezoid, well, what's the slope of this trapezoid? Well, this is the high point, so it's 10. This is 2 units over from that, so that's 5, right? So this green trapezoid, it's 5 here and 10 here. And it's, of course, we're going from now 10 up to 12. Okay, tell me, what's the slope?
5 halves.
Pardon?
5 halves.
5 halves, good. And that's 2.5, of course, but I like the fractions, but it's also a good thing to write a decimal equivalent of the fraction after you write the exact value. If you write the decimal equivalent, then you can kind of see how big the number is. With fractions, you know, how big is 17/93? Okay? You have to think a little bit. See, yeah, it's probably around a fifth. Okay?
Why would the slope be 5 halves?
I'm sorry?
Why would the slope be 5 halves?
Well, it's rise divided by run.
Yeah, but the run is 2 and the rise is 10.
No, the rise
Oh,
isn't 10.
Sorry, you're wrong.
You start here and end here, so the rise is only 5, but I'm glad you said that. We want to correct that, right?
You said you're wrong.
Okay.
Right.
Now, all that's pretty straightforward, isn't it? We're just doing simple numbers. And if they're nasty numbers, you can use your calculator to get the nasty results. But you know, ultimately, you do this in a spreadsheet or with a computer program. Okay? And, you know, show you some things, you know, taking 30 minutes to show you how to use a spreadsheet. Okay, maybe not. Okay, so you got 5 halves here, right? What's the area?
15.
Again?
15.
15.
Where do we find that again?
Well, how did we find the area here? We found the,
Midpoint.
we rearranged this into a rectangle. What's going to be the altitude if you rearrange this into a rectangle? You just cut it at the midpoint here and flop that over, right? So the question comes down to, how high is the midpoint? Well, how high is it here?
5.
How high is it here?
10.
So how high is it at the midpoint?
5.
7.5.
That's the rise. I mean, the height has to be between 5 and 10, right? Since this is a straight line that goes from height 5 to height 10. It's halfway between 5 and 10. What's halfway between 5 and 10?
7.5.
7.5, right? Okay? So you want to have this image of how you rearrange a trapezoid into a rectangle. And then you can always figure out how high that rectangle is going to be. Okay?
So the area is 15?
Yeah. Because now the width is 2, the height is 7.5. So the area is 15. Again, this rearranges into a rectangle whose altitude or whose length or whatever you want to call this, but I'm going to say graph altitude, is 7.5 and its width is 2. Right? 2 times 7.5 gives you 15. And of course, if your mental arithmetic is not up to immediately figuring that out, keep practicing it and keep your calculator far enough away that you got to go to some effort to reach for it. Okay? Start using your head. And you already know how to use your head. You got good heads, but you want to exercise mental arithmetic. You don't have to become an expert at it, but you have to know it well enough to use it as a thinking tool without having to interrupt yourself by punching buttons. Okay? Okay, so there we have it. And that is pretty simple. Okay? So that's how you label a trapezoid. Now, the other thing is, the slope anywhere between here and here, well, the slope, at least at the midpoint, is probably pretty close to that 5 halves, right? Okay? So you were talking about, you know, I asked you to do the slope versus the midpoint of the interval. So we're coming around to that idea. Okay, we'll do a little bit more with it. The other part is, of course, we can just do the original trapezoid that I drew over here that has a width of 1. I didn't want to use a width of 1 because then you're not really using the width. You're not multiplying by anything when you get the area, and you're not dividing by anything when you do the rate of change. But you could use this one, and you're going to be pretty close to, the slope from here to here probably doesn't differ much from the slope of that little segment, right? Okay? Now for any graph, whatever the graph, if we divide it up finely enough, every one of these trapezoids will have an area that's probably 99% within plus or minus 1%, if not within plus or minus 2% of the area under the curve. And the slopes, well, all these little segments of the curve are almost straight. Okay? There's no point where the slope isn't pretty straight. Now that's something you really want to think about, because if you divide this up finely enough, you get a series of estimates that you can put in a table to tell you almost exactly what's going on with this curve at every point. I haven't explained why the area is important. I'm just saying it's the second half of calculus. Okay?
Only the second.
And
half
slopes of the first
calculus
half.
that they start teaching you
Okay.
halfway through the class.
And what we're dealing with here is how to interpret these things. That's what we're after, and how to calculate them approximately, and use that to model the pendulum, to model the flow, to model all this stuff. Okay? Okay, very good.